Have you ever wanted to send an audio signal using a laser beam? Well, now you can with this project. As Earth's orbit becomes more and more populated with satellites, the wireless network connecting the world must evolve to accommodate the increase in bandwidth requirements. Some companies like Elon Musk's Starlink and Toronto's Kepler Space are using optical communication relay networks which use space lasers to transmit data. That's right, space lasers. Starlink's constellation of over 9,000 CubeSats are able to transmit over 42 million gigabytes per day. Let's dive into this topic for a quick lesson on wireless communication. All wireless devices, from radios to GPS, use electromagnetic waves outside of our vision. Let's take a look at the electromagnetic spectrum and what wavelengths are generally used. FM radios generally transmit in 2.8 to 3.4 meters. Shorter distance systems, like Wi-Fi and Bluetooth, use 4.3 to 12.5 centimeter wavelengths. And more long-distance telecommunication systems, like 5G, use 12.5 to 7.7 millimeters. And 6G will use 3 to 0.3 millimeter wavelengths. As the wavelengths become shorter, the frequency increases, meaning the bandwidth increases, and more data can be transferred on such a wave. Light fidelity, also known as Li-Fi, uses the spectrum encompassing visible and near visible light, meaning infrared, visible light, and ultraviolet. These waves cover 1 millimeter to 10 nanometers. Made popular from the TED Talks of Harold Haas, Li-Fi, Haas explains, unlocks a big chunk of frequency within the electromagnetic spectrum not yet utilized by our wireless networks. Visible light can be modulated in several methods, that is to be encoded with zeros and ones, which go unnoticed to the human eye. LEDs, for instance, can send a signal by emitting pulses of light tens of thousands of times, while to us it seems constant. Therefore, semiconductor light sources such as LEDs, which are common, efficient, and cheap, may be used to transmit data. Any light detection sensor can be used as a data receiver, most commonly solar panels, which are quickly becoming more and more common around the world and cheaper to manufacture. In theory, on a sunny day, a solar panel can split up the modulated signal, carrying some internet data while still collecting energy from the sun. A dual-purpose panel without the need for a separate satellite receiver dish. So, why use lasers to communicate in space? Lasers emit light with some unique features which make it a much better option for long-distance data transmission in space. Even if it looks like white or yellow light is being emitted from an LED, they generally emit polychromatic light, meaning a variety of wavelengths. Lasers have the benefit of emitting monochromatic light, meaning they can produce a single wavelength giving it a specific color, usually red, which is about 650 nanometers, green, around 532 nanometers, and UV, around 355 nanometers. Knowing your data will be received in a specific wavelength allows engineers to filter out non-desired wavelengths of light. Another benefit is that most light sources emit divergent light, meaning the light spreads apart as it travels. The reason why your flashlight that's 5 centimeters in aperture will grow to a few meters when shined. Laser light has the benefit of being collimated, meaning it won't generally expand as it travels through open space. This means the energy will not dissipate, and a beam can therefore travel a lot further and remain bright. Divergent waves, which carry private data, can be intercepted anywhere along its beam path, so as long as the perpetrator can decrypt your data, it is not safe. A collimated beam, on the other hand, can be only intercepted along its very small and narrow beam path. Additionally, satellites already use solar panels as a power source, which can serve a dual use as a Li-Fi receiver. So, have I convinced you that laser optical communications is the future? Well, SpaceX thinks so, and so does the European Space Agency, which just awarded Kepler Space a €36 million contract to develop this optical relay network in low Earth orbit, as part of their high-throughput optical network, Hydron program. I've named this simple project Laser Audio Transmission of an Analog Signal. A transmitter converts an audio signal, my voice, into an electrical signal, which modulates a laser emitter. The solar panel on the receiving end generates a modulated electrical signal, which is then played through the speaker. This device showcases how an analog signal can be transmitted wirelessly without the need of an analog to digital conversion, something an audiophile is terrified of. As an example, a Bluetooth system will turn a natural sound from a record player, an analog signal, into zeros and ones in order to send it wirelessly. This LATAS system does not. Therefore, it preserves the natural sound captured in the original recording. Please like and follow to check out the next video where I'll explain how this device works and how I completed this project in 2 weekends. My name is Lior, this is Levy Projects, thank you for watching.